concept of right-derived functors unify many different cohomology theories. In this video, we wanna explain what they are. So let us consider a covariant left exact functor between a billion categories. Recall that these can just be thought of as category where we have good notion of short exact sequences. And recall that when we say that f is left exact, we mean that f preserves injectivity, but not surjectivity. In particular, f does not preserve short exact sequences. The right-derived functors of f help f continue this sequence into a long exact sequence. We can view the first right-derived functor of f as a measure of the extent to which f fails to be exact, and then the second right-derived functor of f measure the extent to which the first right-derived functor fails to be exact, and so on. Well, from homological algebra, we know that given a short exact sequence of cochain complexes, we get an induced long exact sequence of cohomology. This gives us the following idea. Maybe for each of these objects, we can associate a cochain complex, and then we can define the right-derived functors of f in terms of the cohomology groups of these cochain complexes. For example, let's say this is the cochain complex associated to M. Then we can define the ith right-derived functor of f evaluated at M to be the ith cohomology group of this corresponding cochain complex. We just need to make sure that the zeroth right-derived functor of f evaluated at M is actually f of M. Since that will correspond to the zeroth cohomology of this cochain complex, i.e. the kernel of delta naught, we just need to make sure that the kernel of delta naught is indeed f of M. There's an easy way to guarantee this. Namely, we can take any exact sequence of this form and then apply f to it. Since f is left exact, we know that the kernel of this map delta naught here must be fm. Thus, if we define the ith right-derived functor of f at M to be the ith cohomology group of this cochain complex, then indeed the zeroth right-derived functor of f at M is going to be equal to f of M. Now similarly, we can find some resolution of N and L and then apply f to them, thus getting three cochain complexes. Now here you may ask, when we apply f to this exact sequence, the resulting sequence is also a cochain complex. So why did we chop off this part? Why did we only consider this part of the cochain complex? Well, recall that to get a long exact sequence of cohomology, we need a short exact sequence of cochain complexes. But as we said, we do not always have exactness at this level. Actually, that was why we need to discuss right-derived functors to begin with. Of course, that leads to the next natural question. So, how do we know that we'll have these short exact sequences? Actually, what are these maps even? Well, here we'll cheat a bit and just let the En be In direct sum with Jn. Now, since f is additive, which by definition means that it preserves direct sum, we see that each of these sequences must be split short exact. So indeed, we have a short exact sequence of cochain complexes. But do we really? These are cochain complexes, or at least we can choose I and J so that these are cochain complexes. But is this a cochain complex? How are these maps here even defined? We'll answer that in the next video, where we'll see that we need to put extra conditions on the objects in this resolution. Namely, we need to ask that they are injective. Thus, we'll also introduce the notion of injective objects.